Okay, so this is the presentation for digital identity resolution, and it's jointly presented by the two teams. First, I'll talk about the introduction and summary. So nowadays, online marketing has become a $1 million market. One of the most used strategies for online advertisers is to create customized marketing campaigns with data collected from users' online activities. These activities include location, searches, shopping history, career, and possibly income. This strategy is proven to be very effective. However, there are a couple of challenges. One of them is that user data are usually scattered around multiple electronic devices. So although these online activities belong to the same user, they might have very different signatures. So our goal is to find a way to group them together and create a more coherent and comprehensive view of the user's digital identity. Our approach consists of three parts. The first is preliminary grouping with the IP collocation algorithm, and the second is behavior feature engineering, and the third is fine-skill user-level groupings, which is just combination of the first two. Now we'll talk about the dataset and technologies we use.
The technology stack that we use consists primarily of Jupyter, where we did most of our computational work. For graph visualizations, we have used Pybus and GraphFrames. Pybus is mainly used as it is an interactive graph visualization tool, and GraphFrames because it's fully integratable with Spark. We've done most of our work on Spark and using approximately 200 cores. Most of the backend has been handled using Cloudera and Hadoop. Okay, so moving on to the data set, the data that we use is 600 GBs of RTB data. RTB is the real-time bidding data used in advertising as a means to buy advertising inventory. This is done on a per impression basis. Every impression is counted as a time when when any advertisement is sourced. It is not necessarily related to whether it is clicked or not. We use 90 million plus unique devices for our algorithms and 300 plus million unique events. Moving on to the IP collocation algorithm.
Okay, so the IP collocation algorithm is the first step in our solution, and it aims to create a preliminary grouping of devices by the IP address. The key idea is that if two devices, they appear more often on the same IP, and it's more likely they belong to the same group. So the input of this algorithm is data frame made of rows that have 3 columns: device ID, IP address, and timestamp. And the output is a graph where the device IDs are the nodes, they're connected by the edges. You know that these edges, they have weights, float type, and they represent how strongly two devices are connected. So, this algorithm also takes 2 parameters. One is the max, that's the max number of devices allowed on IP at any time. We have this parameter because we want to exclude, say, communities, for example, large corporations that could have more than thousands of computers. And also the next one is the minimum edge weight. If 2 devices, they only share the IP address once after 30 days, we don't want those edges in our graph. So the next one is once we have the IP collocation graph, we can run community detection algorithms to trying to cluster devices into communities. So there are many choices. The one we pick is called LPA, which stands for Label Propagation Algorithm. This algorithm takes the IP collocation graph as an input, and output is a Spark data frame that made of device and community ID. Just to briefly go over how this LPA work. So at the beginning, each node device thinks itself is a community and has its unique community identifier. And at each iteration, it communicates with neighbors. It broadcasts the community ID it belongs to. At the same time, also receives incoming community ID from its neighbors. And at the end of each iteration, the node updates is labeled to the ones which the majority of the neighbor belongs to. And once the algorithm converges, each node will have the majority label of its neighbor. So the next one is the IP collocation algorithm community detection or validation. So for this one, ideally, the best way to validate this algorithm to use the ground truth data. So that means beforehand we know which devices belong to the same person or the same household. But unfortunately, we don't have those data. Instead, we look at other metrics. So one of the metrics we look at is the community side distribution. So here, you look at the graph on your right side. This graph is made with data from July, the 4 weeks. And the x-axis is the size of the community, and the y is the number of the communities. So we can see most of the communities across the 4 weeks in July, they have size 6 to 10. And yeah, and this makes sense because each household has around 6 to 10 devices. So just by looking at this graph and these metrics, we cannot really say the algorithm is correct. To be able to say that, we need the ground truth data. However, by looking at this, what we can say is that our algorithm is not wrong. Next, my teammate Xin will be talking about the performance of the algorithm.
So for performance improvement, we have tried to do it from 3 different perspectives. The first one is to tune the hyperparameter. We focused on Nmax and gamma. As you could see from this graph, its axis is different parts of the function. We separate the whole function into 7 different parts so that we could see how modification affects each part of them. The y-axis is total execution time, and each line represents one Nmax value. This line, you could see from this graph that as long as the Nmax is smaller than 70, it would give a better performance, and for gamma, it's less than 0.8. That also has a semantic meaning. With a smaller Nmax, a smaller gamma, we are actually working with smaller group of data set and giving a faster speed. Another thing abnormal from this graph is that all the different parts execution time is increasing. We conclude that this comes from the reuse of some transform operation. For example, the part 5 uses the part 4's results, then the part 4's transform operation would be reprocessed. We use cache to eliminate those redundant execution time. The final thing we tried is to modify the structure of data stored in data sets. The ID pairs after modification, as you could see from this graph, it's 1/3 compared to the original, which improved the performance largely. The final graph is the total execution time for different metrics. The highest one is the blue one is the original algorithm. It takes very long time, and the lowest purple line is the algorithm after modification. It's about 400% faster than the original. Next, we will cover.
So for the age cluster formation, I'll go ahead. So this is our data that we were talking about earlier. This is the kind of structure that we have. We have the impression logs wherein you can see the advertising ID we have. So the whole data, the whole impressions log is somewhere around 300 million by 54. And then we have the publisher section where we have the IDs for individual publishers and what kind of a publisher it is. And then we have the campaign one. So basically we are trying to match each of these and create a pivot table based on the IAB categories. So now for the IAB categories, these are the IAB categories that we have in the data. And basically we're trying to create pivot tables around it. So yeah. So the pivot table is something like this. As you can see, it's along each ID, and it basically looks like a one-hot encoded pattern on all of the IAB ones and IAB2, etc., etc. And for our implementation, we're basically doing a feature engineering to select specific features for cluster algorithm. Then we're running clustering algorithms to figure actual clusters. Now we are actually using three types of clustering algorithms. That is the k-means, the LDA, and GMM, which like for the results we'll refer the next slides. Then once we do that, we actually run a validation technique, a cluster validation technique, which tells us if the cluster is stable or not. So if the value, it's called the Celote index, and if the value is close to 1, then the cluster is pretty much stable. If it's less than 0, then it's unstable. And then we check out the data balance among each cluster, if it's appropriate or not, which I'll talk more about while talking about the GMM algorithm. And then we actually reverse engineer the cluster category based on the IB types. So apart from this, we also tried a bunch of other approaches, that is PCA and enhanced KNN. But PCA, it does some sort of a dimensionality reduction, but it didn't make sense to do it because we are anyway cherry picking individual features and the data is very sparse. So PCA wouldn't be a good choice for it. And for the enhanced KNN, we were hoping to get some validation data, but since we did not have any, we just dropped this algorithm. So these were the results for the different clustering algorithms. As you can see, for the k-means, one of the cluster has most of the IB categories in it. So it basically suffers the curse of dimensionality. Even for more than 10 features, it starts failing. Now GMM and LDA basically have Bayesian approaches, but in particularly GMM does a soft allocation of sorts to each value. Now this is a problem since sometimes one of the GMM cluster would completely miss out all the values and there would be just 2 clusters. So this was a recurring issue. And we went ahead with LDA. Another benefit of using LDA was that LDA accounts for the occurrence of different features rather than just the count of it. I mean, rather than just having it. So, and also LDA results were pretty much stable throughout all the data interaction that we did for like 7 days, 15 days, months. So yeah, so we went ahead with LDA. And this is the LDA result analysis to figure out what actually the cluster corresponds to in terms of age. So as you can see, for parenting, the cluster 2 is 62.3 and cluster 1 is 36.8, whereas the cluster 3 has 0 interest in this, whereas the cluster 3 over here is like a lot interested in games, that is the video and computer games category. And similarly, you can see for all of these cluster divisions. Now at the end, we just infer from this information that it's a reasonable guess that the cluster 1 is young adults, the cluster 2 is elder, and the cluster 3 is kids and teenagers. We further performed some sort of a validation on it, where on the trained model, we ran the next few days of data and we got a 80% accuracy on it by using the same IFAs, if the same IFAs are landing up in the same cluster. So yeah, this is it. And I'll hand over it to Brian.
Okay, so there are 2 visualizations in our final project, and let's directly go to the demo. The first graph is the community detection graph, and the nodes are the device IDs. The edges is the relationship between them, and the color represent the unique communities. Also, the width of the edge represent how strong the relationship is between 2 nodes. And so the formation of this graph is based on the IP collocation algorithm and also the graph algorithm. And we select 7 different communities to show here. So for example, this community here, the green community, so how does this node connected to, since this node is connected to all other green nodes here, it is really obvious that this form a single community. And sometimes there are nodes that are connected to 2 different colors of nodes. For example, but because this red nodes, it connects to more red nodes than to this single pink nodes. So this nodes will also belong to the red community. Okay.
Okay, for the next one, we also have the age categorization in the graph visualization. So if you see this particular cluster, the blue ones basically represents the elder adults and what kind of an app they use. And the red ones accumulate for the young adults, and the green ones basically for the kids and teenagers and what kind of an app usage they show. So yeah, this is it for the demo. No, you can trim it out, it's nothing to worry about.